All right, well, let's get into Module 2 here, which is divided into two parts. In Module 2, we're going to be discussing so-called descriptive statistics. First, in the first part of Module 2, we're going to take a look at graphical representations for descriptive statistics. And then in the next part, we'll take a look at numerical mechanisms for descriptive statistics. Later today, we'll get started in Module 3, in which we'll take a look at probability. Then in Module 4, we'll be prepared to do some inferential statistics, and finally regression later in the course. Okay. So a picture is worth 1,000 words, as the saying goes. And if you're going to be doing statistics, in fact, the very first thing that you should always do with any data set that you have to work with is to just look at the data set. Do a so-called scatter plot or a histogram or whatever, just to get a general notion of whether the data makes any sense or seems to have some outliers or what have you. So, we're going to take a look in here just at histograms and box plots. There are many other mechanisms for doing graphical statistics, graphical descriptive statistics, but we only want to take a look at a couple of the most useful approaches. The idea of histograms is that it makes it relatively easy for you to identify average values and whether there is some kind of hump shape or bell shape to the data, and also to identify whether the data is skewed or lopsided in one direction or the other. Box plots are much more detailed in terms of the graphical representation that they describe. You can identify so-called quartiles, that is the median value where half of the data is less and half of the data is greater. You can also identify the lower quarter and the upper quarter of the data. You can identify outliers in the data, skewness of the data. Also, it makes it easy to compare two distributions of data side by side to see whether the two are appear to be the same or appear to be different from each other. We're first going to look at data from a fast food restaurant experiment, and this was an actual experiment that was done by a group of people from statistics at Carnegie Mellon. The location was some unnamed fast food restaurant in Pittsburgh near campus. This unnamed fast food restaurant is actually the Subway shop on Craig Street, but don't tell anybody. And what they were interested in is determining whether informing people buying lunch about calorie information changed their calorie consumption relative to what they would have consumed if they had not been presented with this information. Okay, so we're saying here that hopefully the calorie consumption was reduced, but actually that's a side test, if you will. We mainly want to determine whether the calorie consumption changed in a statistically significant way. Okay, so someone walks into the store and is asked, do you want a free lunch? Now, if you walk into a restaurant where you plan to buy some lunch and you are asked if you would like a free lunch, then unless you are a particularly suspicious kind of person, you're going to say yes. So anytime someone said yes, then randomly that person was either given calorie information about what was available in Subway or not. All right, flipping an invisible coin, whatever. People were just chosen at random to receive the calorie information or not. Then we, or the people who did the study, would analyze the lunch that the person bought, the lunch that each person bought, and based on information from the store, they would be able to know what the total amount of calories was that each patron consumed. Okay? Now, in addition to checking the lunch that the person actually obtained for calories, other demographic information was asked as well, such as, how hungry are you on a numeric scale? Are you dieting or not? What is your weight? What is your age? These kinds of other demographic things as well. Now, if you plot a histogram of the weights of the patrons involved in the study, here's what you get. Well, actually, this is a little bit more than what you actually get. So let me pull up this fast food experiment in aisle, and we'll do the same thing I showed at the end of my previous lecture video. We're going to look at the weights of the patrons. Show a histogram of the weight of each patron. In a histogram, you have to decide how wide the so-called bins are to create this this plot of the count or the percentage of the number of people in each of the so-called bins. We're going to allow aisle to do this for us automatically, and I'm going to generate this histogram. And there we go. Okay, so the histogram we have here is essentially the same as what we have in the notes. There does appear to be some minor discrepancy. Frankly, not sure why. It may be that the buckets are the same widths. Okay, in any event, we see that the weights are sort of grouped around this 160 to 169 level. That seems to be the most common weight. Some people, a diminishing number of people weigh less than that, a diminishing number of people weigh more than that. And we do have some so-called outliers to the right of that distribution of weights. People up around 250 pounds, 300 pounds. Looks like one person up above 320 pounds. And this is referred to as both the left side and the right side of the histogram are referred to as the tails of the distribution. We would typically see most of the weights around some central weight, with numbers tapering off to lower values and upper values. Okay? And it turns out if we request to see some numerical statistics, in particular here the mean, we can select weight as the variable that we want to get this mean for. There are some missing values. I want to show you those. Let me hide the toolbox. Notice that in the weight column, there are some stars that appear. These are individuals involved in the study where either they declined to give their weight or the person interacting with the customer forgot to ask for the weight. All right, and we can't compute a mean involving these so-called missing values, which is why we, come here, statistics, oops, lost my stuff here. So mean, I want the mean of weights, but I don't want to include missing values, which can't be used in the calculation. When I hit calculate, I see the mean over here in my output area. And as indicated in the slide in the notes, the mean here is about 163 pounds. N here is the number of records, the number of people involved in the computation of this mean value. Okay. All right, so that is histograms. They do give you a sort of quick visual description of how the data are distributed. They give you an idea of whether there's a, whether the distribution has an obvious sort of center with declining left and right tails. Gives you an indication as to whether there are some so-called outliers, but it's really not very precise. And in fact, if I go back to the histogram here, one of the big problems with histograms is that binning is kind of arbitrary. And if you select a bin size that's too narrow, you get a really choppy looking histogram. And on the other hand, if you select a bin size that's too wide, you don't get any differentiation. Okay, so it appears that by automatically choosing bins, the aisle went ahead and chose 10 bins that were 10 pounds wide. But if I choose bins that are, let's say, 4 pounds wide, whoops, this is hunger, not weight. So let's do weight with bins that are 4 pounds wide. Then we get this really choppy looking histogram, which would only really look reasonable if we had a much larger sample size than just the 600 or whatever it was that we got. And on the other hand, if I choose a size that's too wide, like if I choose a 25-pound bucket, then I don't get really much, I don't really get enough detail in the histogram. So histograms have various problems. A much better approach to visualizing a distribution is to use what are called box plots. And to talk about box plots, we need to introduce some more concepts. Okay, so a percentile in statistics is the percentage of observations that are below some value. Here, our maximum weight, let's go back to automatic binning. Okay, and I've also redisplayed the mean of the weights, not so much because I care about the mean, but in this case I want to see the total number of samples in the set of people. So there are 627 people represented in this histogram. The topmost weight bin that we have has got 2 people in the range from 320 to 329. So the percentile here would be 2 over 627, represented as a percentage. So that's about, what, about 99.7 percentile for those top 2 people. And then in this range here, since we know that the mean is 163, that would be in the vicinity of the median. Okay, the true median is the so-called 50th percentile. Half of the people weigh more than the median, half of the people weigh less than the median. Now, by convention, it's common to break these percentiles into quarters. And we can talk about the bottom quarter, the top quarter, and the second quarter and third quarter here. So the first quartile, so-called, is the 25th percentile in our data set. That is 25% of the values in our data set are below this first quartile value. 50% are below the second quartile value, or the median, and 75% are below the third quartile value. Now, we call the middle two quartiles the interquartile range, or IQR. So from the 25th percentile to the 75th percentile, that is the middle 50%, the middle half of the observations. And so in our histogram here, more or less the middle quartile would be from, somewhere around 120 up to somewhere around 180 or so. Sorry, I said the middle quartile. That isn't correct. The interquartile range, going from the 25th percentile up to the 75th percentile, would be somewhere in that vicinity. As a much simpler example, let's suppose that we have this example data set, maybe of scores on a quiz or something like that. And if we sort the scores and display them, we have 1, 1, 2, 2, 2, 3, 4, 4, 5, 6. So there are a total of 10 values here, a total of 10 scores. The median, when you have an even number of values, is halfway between the middle two. All right, so this 2 is just below the median, and this 3 is just above the median. And so we compute the median in a case like this by adding those two values together and dividing by 2. So even though the specific value 2.5 does not appear in this data set, we say that the median for this data set of these 10 values is 2.5. That is, 5 of the values are below 2.5, 5 of the values are above 2.5. In each half of the data set here, below the median and above the median, conveniently there are an odd number of values. All right, so below the median we have 1, 1, 2, 2, 2. Therefore, the middle value here, this 2, is exactly the 25th percentile. And the middle value on the other side, on the high end, 3, 4, 4, 5, 16, this 4 here is the 75th percentile. So what we mean by that is that half of the values from the 25th percentile up to the 75th percentile, that is the interquartile range here, is from 2 to 4. And the width of the interquartile range is therefore 2. Okay? Now, we can draw that interquartile range by drawing a box. Whoops, getting my highlighting goofed up here. So the box here starts at 2 and goes up to 4. that is the interquartile range for these weights. Okay, half of the weights are between 2 and 4. Within the box, the median is indicated by a darkened line. So the median, as we remember, was 2.5, the value halfway between 2 and 3 here. All right, so the median is not right in the middle of this interquartile range. It's closer to the low end of the interquartile range. And then we also need some way of representing the bottom quartile and the top quartile. Okay, so let's talk about how that's done in a little more depth. We have our interquartile range represented by this box. Okay, so the box contains the middle half of all of our data. Now, just arbitrarily, okay, the fellow who originated box plots was a fellow named John Tukey. Let me pull up some information about him, if I may. Okay, so here is our buddy John Tukey, one of the most, if not the most, influential mathematical and theoretical statisticians of the 20th century. Okay, I guess that's impressive. He is the fellow who originated the idea of box plots, and his feeling was, all right, if we have a box representing the middle half, then the upper quarter and the lower quarter may be more stretched out than that middle part. So let's have the upper part in our box plot, the so-called whisker of the box plot, extend out to be 1.5 times the width of the interquartile range. And likewise, on the lower end, we'll also have 1.5 times the interquartile range. Okay, we expect the 50% of the data around the median to be somewhat compact, and we expect the upper quartile, and the lower quartile to be somewhat more spread out. Okay, so what we do is we create these so-called fences at the high end and at the low end that are 1.5 times the width of the interquartile range, above the 75th quartile and below the 25th quartile. Now, there may actually not be any data at the location of those fences. So what we will do to represent the so-called whiskers is to pull back that upper fence until we encounter an actual data point. Okay, and that actual data point will be the upper end of our so-called whisker. Similarly, on the lower end, we will pull up the lower fence until we encounter an actual data point. Okay? Now, in this particular diagram, it turns out that the smallest value that exists in our data is within the fence. Okay? So there is no data that is outside of that 1.5 quartile range fence. But for the upper values, for the upper data, remember we're using our customers' weights as an example, we do have some outliers. And those are represented by dots or X's or stars or whatever your plotting software decides to do. So for aisle, what we get when we do this for the weights looks like so. The middle interquartile range goes from a weight of looks like about 135 or so up to a weight of going to guess around 180 or so. So from about 145 up to about from about 140 up to 180, half of the people are in that range. Then in the lower quartile, the lower 25%, the lightest weight person that we have in our entire data set is around 90 pounds. We have nobody lighter than 90 pounds. So the entire lower quartile is contained and described within this so-called whisker. On the upper end, we do have some outliers. We do have some people that are above 250 pounds. Okay, so by using a fence that is 1.5 times as wide as the interquartile range, and then pulling back to an actual data point, somebody's actual weight, there we have the whisker. And beyond the whisker, we have outliers. Okay? So this, it's a simple plot. It's a simple image. And yet, it does a vastly, vastly, vastly better job of providing intuition about what's going on with this data set compared with the ordinary histogram. We have the median, this line in the middle of the box. We have the interquartile range, the middle 50% of the data points. We have the lower quartile, and we have the upper quartile. We differentiate people in the upper quartile who are more than 1.5 times the interquartile width away with these dots. And so we can see that on the upper end, we have some outliers where an outlier here is just defined to be someone whose weight is more than 1.5 times the interquartile range above the interquartile range itself. Okay. So, thanks, John. Okay. So, the box plot is arbitrary. It was just invented by this guy, John Tukey, and yet it does, it wasn't invented arbitrarily just for the heck of it. It does contain a very clean, very thorough summary of what's going on with our data set. Okay. Let us, in fact, do where are we? Oh, box plot. Let's do a box plot of the weights of our people. Vertical orientation. And there we are. So we have the same plot appearing here as what's shown in our slide. And the plot is nicely interactive. We can actually see, if we point at the plot, that the minimum weight is 91, the maximum weight is 325. The lower fence is also 91 because that's both within the that's both within 1.5 interquartile range widths, and it's also the lowest value. The interquartile range goes from 138 pounds up to 180 pounds. I think I had said from about 140 to about 180, just eyeballing the plot. And the median value here is 160. Okay, now the upper fence is at 240, and then we have outliers above that value of 140. I can also do this horizontally, which I actually find easier to think about because I'm used to having my data values on a horizontal axis instead of a vertical axis, but obviously, you know, whatever you prefer is fine. Now, here we're doing some side-by-side box plots of the people who did not receive any calorie information versus the people who did receive calorie information. And we're asking a question here. Does providing random people with calorie information appear to reduce their overall calorie consumption? All right, so at this point, since this is not a live class, I'm tempted to do the Jeopardy waiting song. Do 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 do. Okay, I'll stop now. So, does it appear that people who received calorie information consumed less than people who did not receive calorie information? Based on these box plots, the answer appears to be yes. For one thing, the interquartile range for the people who did not receive calorie information is clearly higher than the interquartile range for the people who did receive calorie information. Likewise, maybe even more impressive, the median value for people who did not receive calorie information is noticeably higher than the median value for people who did receive calorie information. Okay, so yes, it does appear, all else being equal, that people who received calorie information did consume fewer calories on average than those who did not. Now notice that the whiskers, the fences out here were the same. So, you know, some people who received calorie information didn't care, just ordered what they usually ordered. Okay. What about weights? Because the selection of whether someone received calorie information or not was purely randomized, you know, flipping an invisible coin or something along those lines, there should not be any difference in the weights between the people who received calorie information and the people who did not. And let's see if that's true. So here we have the box plots. All right, so let me just be clear here. Here is the histogram of the weights, and here are the box plots for the calories consumed. So maybe that's a little misleading. Here are the box plots for the weights of the people in the two groups. Those who did not receive calorie information and those who did receive calorie information. Now, the weights of these two subsets of people don't appear to differ particularly. The median weight of both groups looks to be almost exactly the same. There's not much difference in the interquartile range for the people who did not receive information versus those who did. The low end is about the same. There is some difference in the upper end, but that's just due to, you know, the particular data set that we got. We did evaluate over 600 people. As we evaluated more and more and more and more people, we can imagine that these two box plots would look more and more and more and more alike in terms of their fences and outliers. All right, so that concludes our graphical discussion, or our discussion of graphical descriptive statistics. Histograms are very popular. They are fine. Box plots are much nicer once you understand how to interpret them. There are lots of other graphical representations of descriptive statistics that we just simply don't have time to get into. Okay.